Today, I have two things I want to talk about. The first thing is I want to finish up LQG. More specifically, I want to talk about steady-state LQG problem. Over here, we have several nice properties I want to mention. And then afterwards, I want to talk about feedback design in the frequency domain, which is, for some of you, it might be a review of loop shaping classes. For some others, it might be completely new. Let's see how it goes. In the last lecture, we talked about this separation theorem in LQG problem. And it's kind of nice. It's saying LQG is nothing but designing a Kalman filter and then designing a regular LQ controller. And this Kalman filter and this LQ controller, based on this separation principle, can be designed separately. And if you recall the equations for the Kalman filter and the equations for the LQ optimal controller, you will notice that the Kalman filter equations are totally independent of the LQ control equations. And the big reasoning behind this, as you can see, is because Kalman filter is nothing but an observer, a special observer, and LQ is nothing but a state feedback control. So this is a special observer-based state feedback control law. The separation principle is independent of whether these are time varying or steady state conditions. Of course, we will be mostly focusing on the steady state problem. One reason for that is because it's convenient for most practical cases. It's convenient in the sense we can use constant state feedback gains and steady state Kalman filter for stationary LQG problems. Okay? This is the assumptions are exactly the same. The system is time invariant. The weigh-in matrices in the performance index, like Q, R, S, they are time invariant. And the noises, V, W, they are white noises, Gaussian, okay, white sense stationary. I did one thing differently. In the stationary LQG problem, you are very familiar with the first term. We want to take a look at how the system behaves if I take the cost function, the summation, to be infinity. Okay, here. That's the usual, the thing we have seen before, the usual steady state optimal control problem. But here, we did something slightly different. We put a scalar gain in the cost function. We divided the common j by n, and this n is going to infinity. This is because, think about the regular case. J equal to expectation x transpose n s xn plus 0 to, let's say, if this n is going to infinity, so n is going to infinity. Can someone tell me what will happen to this cost function? What will this j be? Infinity, right? Why is that? This is a tricky question. Why would this go to infinity? That is not quite true. Actually, no, that's roughly true. Yeah. Can someone have another guess? That is explaining one phenomenon. But the true reason behind that, there's some deep reasons behind this. Deeper, a little bit deeper. So you know that the system is subjected to noises. That's why we need the expectation sign. Okay? And whenever you see quadratic terms of some signals containing noise, you know it's sort of containing the covariance matrix inside of the second moment stochastic property of the noise is contained in this cost function, which is non-zero. For example, I think the best way is to, if you take out your notes from last time, the best way is to take a look at the equation for the cost function. Yeah, the best way is take a look at last time, how the cost function looked like. So it contains two parts. One is j hat, another is this summation term. As you can see, these are the estimation error covariances, right? Z, they are non-zero. Also, you take a look at here, estimation error covariance is non-zero. And inside here is this is a big quadratic function, and this one is a positive definite. So you see, it's a summation of a bunch of positive terms. If we take this signal, take this number n to be infinity, these will be summed up to infinity. So the reason for that is because the system has these noise terms, and this noise will accumulate in the states. When we take the expectation, we will get the stochastic properties, second moment to be more exact, of these noise terms. If we don't take any actions, this cost will go to infinity for n to be infinity. So we needed this n here divided by n. And actually, it turns out the result becomes very nice if we do this. Think about in a stationary case, if everything has settled, if I divide this summation by capital N, it looks like actually due to the law of large numbers, this becomes the expectation of something. This becomes the expectation of the current optimal cost, current second order quadratic cost. Okay? And this structure looks convenient for analysis. So in this sense, you see now, for the stationary LQG problem, we are minimizing the mean on average of these quadratic terms. That's the intuition behind this. So someone tell me, if I add this n here, will the solutions change? Like my optimal control law, U optimal, and then the common filter equation. Will these solutions change because I have added this n? No, right? Because this is a scalar. So scalar doesn't change optimality of the solution. I can use exactly the same control law and the common filter for this case. The only difference is now these matrices are constant. S, Q, R, these are constant. And then we have this here. We have the convenience of, we have now constant state feedback, okay? Because it's a stationary LQ problem. So Riccati equation converges to the algebraic Riccati equation. So the first part is for LQ problem. And then the second part is we have this steady state common filter problem, where we also have the Riccati equation, algebraic Riccati equation, and the constant common filter gain. These are convenient in the sense of implementation in practice. Okay? As a review, the convergence conditions for the Riccati equations are the controllability conditions, observability conditions. But in this case, there are, if you take a notice here, I have ABW has to be controllable, and AB has also to be controllable. So think about which one of these is for the LQ problem, and which one is for the common filter. What about the first one? Is for common filter, and the second one is for LQ. It's easy to see because BW is for the noise, so it's for the common filtering problem. Okay? And then second, ACQ. CQ is defined by this. ACQ and AC has to be observable or detectable. So similarly, AC observable or detectable is for the LQ problem. And no, ACQ is for the LQ problem, and AC is for the common filter problem. Under these steady state assumptions, you know that the common filter will converge to a steady state, and the common filter dynamics is stable. Also, the LQ will converge to a steady state LQ, which is also stable. Now, the separation principle comes to take role here. The separation principle says the closed loop eigenvalues come from eigenvalues of the LQ feedback and eigenvalues of the Kalman filter. We have just explained that the Kalman filter in the steady state is stable. So this dynamics is stable, and this dynamics is also stable because of its optimal LQ control. The stability condition is that for LQG problem, we have guaranteed closed loop stability, Kalman filter stability. The system as a whole is stable. And if you want to know detailedly how the eigenvalues look like, you can take a look at these eigenvalues. So this is for the LQ, and this is for Kalman filter. If you want, you can write down this. If you can derive this optimal cost, but we won't do it here. The derivations are provided in the cost reader. So this is the end of discrete time LQG problem. Next, we're going to talk about the continuous time version of the LQG problem. A quick summary of the continuous time LQG problem is that everything, the LQ problem here and the Kalman filter problem here are exactly the same as the continuous time Kalman filter and continuous time LQ. This is just the combined version of these two concepts together. And the derivations, so the cost is like this. Now, instead of summation, we have integration here. The derivation of the solutions are, in the big picture, is kind of a limit case. So it's derived by taking the limit of a discrete time LQG problem. Then we get the continuous time version. The derivations are not required in exams. You would just need to understand how the solutions look like. So the solution contains two parts. The continuous time LQ, which is using this optimal control, state feedback control law. This is, so you see now, it's Kalman filter state feedback. And the Riccardi equation. And the Kalman filter is exactly a standard continuous time Kalman filter with the Riccardi equation and the gain matrix. Okay. As a summary, we have now, for the LQG, summary of LQG problem. You need to understand what is LQG, what kind of cost, for example, is minimized in LQG, and why we have to do LQG. Why can't we just do a regular LQ? Okay? If you got the picture in detail, then this is, you know, how the stochastic control with exactly no state is just a common regular LQG with noise in the system. And then if I don't know in exactly no state, this becomes an LQG problem. Today, this is talked about today. We talked about steady state LQG and the continuous time LQG problem. So here, what I wrote down is the not stationary case. I didn't take this to infinity, but similarly, you can define that version. So if you let it go to infinity for this one, go to infinity, then similarly you divide it by a t, which is also going to infinity. Okay. So any other questions?